Okay.
Okay, thank you. Okay, hello everybody, and welcome to another seminar of our series with IFIMAC plus ICMM seminar series. I'm Ramon Aguado, and today I will be chairing this seminar. As usual, the talk is being recorded in YouTube, and you will be able to ask questions after the talk. So if you have questions, you can raise your hand afterwards, or just write your question in the chat. All right, so let me introduce our speaker today. Today is my great pleasure to have with us Eduardo Lee from IFIMAC here in Madrid, in the Universidad Autónoma campus, UAM campus. Edu, as we call him, is an expert in low temperature experiments, transport experiments, in nanodevices, and more broadly mesoscopic systems and mesoscopic physics. Let me say a few words about him and his career. He did his PhD in Stuttgart in the Max Planck Institute for Solid State Research. He defended his PhD in 2009, and he was focusing on scanning photocurrent microscopy of carbon nanotubes and graphene systems and devices. And there already, during his PhD, he accomplished a very important result, which was the first measurement of photoinduced current in graphene. Then he moved to Grenoble for a postdoc, where he changed a bit subjects, and he focused on low temperature transport in nanowire devices, in particular in hybrid semiconductor-superconductor devices under the supervision of Silvano De Franceschi as I say, in Grenoble in CEA. Then he was there for a few years, 5 years or so. He got a Marie Curie fellowship while being there in Grenoble, and there he published a very important paper in the field of hybrid semiconducting system, in particular in the context of detection of Majorana bound states and so on, which was the first demonstration of spin splitting of Shiba states in nanowires coupled to superconductors and containing quantum dots, physics of quantum dots in these superconducting systems. And then since 5 years ago or so, he's been here in Madrid in our campus. He got an ERC grant and a Ramon y Cajal fellowship, which are prestigious fellowships, both of them in here. And with the grant, he started a new lab. He built a new lab focusing on these low temperature properties, low temperature transport lab. And the lab is already running and producing very nice and interesting results. And today he's going to tell us about some of their results, focusing on Joule heating of these hybrid semiconducting superconductor nano. So with this, I finish, and please, Edu, the floor is yours, and thanks again for giving us this talk.
Well, first of all, thank you, Ramon, for the very kind introduction, and thanks for the organizers of this joint seminar series for inviting me. It's a very great pleasure, after years of setting up the lab, to be able to show you some of the results we have been producing in Madrid. And as mentioned by Ramon, well, today my talk will be focusing on some recent work we're doing dealing with the Joule heating effects in hybrid superconductor-semiconductor devices. I mentioned here that the experiment was mainly carried out by 2 PhD students, Angel and Mario. We have used the material from Copenhagen provided by Thomas and Jesper, and we had theoretical support from Gorm and Alfredo, also in our university. So as a starting point, I just want to give a motivation of hybrid superconductor-semiconductor devices. So let me see. Okay. Yeah. Let me start by saying that, perhaps most of you know, it is a material platform that has been widely studied in the past decade. owing to prospects of applications both in topological and trivial quantum computing. So here I put like a schematics that appears in this review paper by Elsa. Of course, a lot of the research in this field really got boomed with these predictions of the realization of a topological superconductor using these material combinations. So let me just start by showing you a bit of the early research in this direction towards a topological superconductor. This is the first experimental paper from Delft, and I just wanted to point out something that will be recurring in my talk, which is disorder. So over here, this again is the first experimental result where signatures of Majorana modes were published, and essentially by applying a magnetic field in this hybrid superconductor-semiconductor device, a zero bias peak was observed, and this was taken as an indication of the demonstration of Majorana zero modes. I just again point out that here the observed superconducting gap was far from looking a BCS gap, so there was this problem in the early days of so-called soft gap, and this was already indicative of disorder in this kind of system. In recent years, or in the past years, there has been a substantial improvement in the quality of materials. This was in a large part driven by this kind of epitaxial growth of superconductors on top of semiconductors, which was able to solve this soft gap problem. And this really enabled a new generation of experiments using this epitaxial hybrid superconductor-semiconductor nanowires that led to very interesting, beautiful experimental data on experiments both directed towards, again, searching for topology, or also for demonstrating quantum devices in the trivial regime. However, in spite of this improvement in materials, it is arguable that still each device is quite different from one another, and that the disorder is still quite present, and this is still limiting the applications in quantum technologies. So, in spite, what I want to say here is that in spite of this improvement in materials, there is still a need actually for different characterization tools that enable us to observe underlying problems with this kind of devices, and in an efficient way that can also give us feedback to understand what are the devices that we're measuring, and also to allow us to detect disorder or imperfections. So I want to go back to this schematics that I showed in the beginning, also to show here that this type of systems have been studied by different types of techniques. In the beginning, mostly tunneling spectroscopy. This is really DC type measurements. Over the course of the years, there has been more techniques using high frequency, like microwave spectroscopy or Josephson spectroscopy. And in this talk, I want to tell you about the different technique that we have been studying, and that is based on the Joule effect. So I want to convince you this talk that we can use Joule heating as a spectroscopical tool, and I will tell you what kind of spectroscopic information we can get from this type of measurements. So as a whole, we have been calling this type of measurement as Joule spectroscopy, as it's based on the Joule effect. And again, I will try to convince you that it can give us complementary information to the other techniques, to DC transport and microwave spectroscopies, and it's quite useful as it enables us to obtain information of both, or of all superconducting leads in the device independently and in the same measurement. Moreover, the information we get, again, I stress, is complementary, so it's not information we can get directly from, for instance, low bias transport. And the main point I think that I want to get to is that by applying this technique, we can get very quickly a device fingerprint. So as I mentioned before, each device is quite different, and by using this technique, we can really get a good idea of what the device constitutes. And also, as I mentioned in the beginning, we will see that there's still a lot of disorder and imperfections in this kind of devices that arise both due to intrinsic and to extrinsic effects, as I will comment in more detail. So we're talking about Joule effect, and when one thinks about superconducting devices, it's not the first type of effect we would think, right? So we don't usually think of dissipation when we're talking about superconducting devices, but in fact, I mean, this kind of effects have been studied already for some time in metallic superconducting devices. So here there's an example of a metallic SNS Josephson junction, and this is quite a nice experiment in which they are able to measure the temperature of the normal part of this device as transport happens, right? So they bias a current, and as expected, like one sees a supercurrent, so a dissipation current, and this dissipation current, of course, doesn't generate heat. However, as soon as the critical current is reached, so one goes now to the dissipative regime, and you can see here that the temperature of the normal part of the device heats up quite substantially. So it goes from around 50 millikelvin to 600 millikelvin. So this shows already that heating can be quite substantial, and this, in this kind of device, leads to the appearance of this kind of hysteretic behavior. Another example is this other paper here, and over here, due to similar Joule heating effects, they observed missing Shapiro steps when they apply microwaves to also SNS junctions. So we're going to look into also heating effects, but now in hybrid superconductor-semiconductor devices. And not only will I try to show that heating effects are indeed important, but that we can also extract interesting information from it. So our devices are, they look like this cartoon over here. So what we do is we get this indium arsenide nanowires, which are covered by an epitaxial shell of aluminum, which is our parent superconductor. Right now, I will just comment that these wires are fully covered by aluminum. So this is what we would call, or the community would call, full shell nanowires. Right now, this is not important, but I will get back to this later on. So what we do is that we deposit these wires on silicon chips, and we etch a small segment of the aluminum shell so that we create a Josephson junction here. So here's just a semiconducting weak link that we can also tune with the gate voltage. And for the first device that I will be describing, we contact these wires with lithographic leads, and these are made by aluminum, so they are also superconducting. Now, let me tell you a bit about the working principle of this technique and what kind of, yeah, exactly, how does Joule heating play a role in this kind of device? Well, as in the case of the previous example of metallic superconducting devices, when a supercurrent flows across the junction, well, there's no dissipation, so there is no Joule effect. But as soon as we reach the dissipative branch, then actually we get heating, well, it's essentially normal Joule heating. So with a power that's proportional, well, that is equal to the current that flows across the junction times the voltage drop. Now, here is the interesting part, right? This is something that we didn't think before, but it's actually quite interesting. So we start generating heat, and to understand how this will play a role in the temperature of the device, we have to consider also what are the heat dissipation mechanisms. So we generate heat at the junction, and some heat dissipation mechanisms would carry some of this heat away. Turns out that at low temperatures, all heat dissipation mechanisms are inefficient. So this actually will create a heat bottleneck, as I will point out. So I will just comment on the main a heat dissipation mechanism for our devices, which is heat being carried by positive particles. Or equivalently, if we thought of a normal metal, in a normal metal, heat would be carried by free electrons. Now, the problem is that when we're dealing with superconducting leads, there is an energy gap, so we don't have these free electrons to carry the heat. So this is what creates a very severe heat bottleneck in this kind of device. All heat that is generated here at the junction, really most of it cannot escape because of this absence of efficient heat dissipation mechanisms. And what's going to happen is that, well, temperature will rise along the junction, and a temperature gradient is, we can calculate what a temperature gradient along the device. If Joule heating becomes more severe, these temperatures actually can surpass the critical temperature of the superconductor. And as a consequence, the superconducting leads will go through a superconductor to normal transition. So this is actually the working principle of the technique that I will be telling you about today. Now, we're measuring transport. So one interesting, or an important aspect to consider is then how does this heating affect the transfer response? So while we're ramping up current and voltage and heating becomes more severe, how does this impact the transfer response? Now here I plot some experimental data of a device like the one I was describing before. And first, I just show you the low voltage range. And here at low voltages, I just wanted to point out that experimentally, when we're studying these kind of systems, we're used to look only at this kind of low voltage range. That's where we see transport that is impacted by mechanisms that involve superconductivity. For instance, as a zero voltage here, you see a very high conductance peak, and this is actually the supercurrent, the Josephson current. Which is not dissipated, as I told you before. And then there's a sequence of peaks, and this we can ascribe to multiple undrafted reflections. So typically, and we as well, when we started measuring this kind of devices, we typically just look at this part of the curves, because that's where we thought all information is contained. Well, as I will show you later on, there's actually quite interesting information when we go to higher voltages. Now, the second point I want to make here is that heating up to this point is not so severe, but there is already heating, and this is also important and it should be considered. So I will get back to this point later. So right now, the curves I show, they're somewhat regular. I mean, every group measures things like this. And let's see what happens then as we crank up the voltage. Just to finish this description here of the low voltage response, apart from Josephson current and multiple underdraft reflections, another thing that we can clearly see is that for voltages above 2 delta, the IV curve becomes linear with well, the slope being the normal resistance of the junction. But if we extrapolate this to zero voltage, it doesn't go to zero. This is what is known as excess current. And this is resulting from the underdraft reflections that occur at the nanowire superconducting interfaces. Now, let's see what happens as we increase the voltage. Well, as you can see, as we keep on increasing the voltage, this linearity of the IV curve starts to deviate. And at some point, we see it going back to linear. This coincides with two dips that we see in the conductance that we measure, the differential conductance that we measure by locking. So what is going on over here? So when the EV curve starts to deviate from this linear response, this is reflecting that the Joule effects are intensifying. So actually the temperature of the junction is increasing, and this will decrease the excess current. So we start seeing a suppression of the excess current. Following these two voltage dips here, we see that the excess current goes to zero. So this actually is signaling that we have killed, let's say, the under reflections of interfaces. This is really pointing that both superconducting leads actually have gone to the normal phase. So they have become normal metals. So to summarize here, the main fact that we measure is that as we crank up voltage or current, Joule heating becomes more intense, and this essentially turns both superconducting leads to the normal state. And the transitions can be seen here in the differential conductance as voltage dips. So this is a transition of one of the leads to the normal state, and the second dip is a transition of the second lead to the normal state. So let me point or just comment that there has been some previous work in this effect in graphene junctions. And so these are also very interesting papers. Now, I hope I convinced you that, by measuring transfer, we can actually detect the superconductor to normal transitions. But also, as I mentioned in the beginning, we want to extract information from this kind of transitions. And it turns out by using a very simple modeling, we can see that the voltages at which these transitions take place, they bring a lot of information. So the simple modeling is really just a heat diffusion model in one dimension. So we consider, let's say, this superconducting lead here, which is one dimensional. And on one side, we have across the wire, we have a temperature gradient. And so just applying a heat diffusion equation, we take into account the thermal conductivity of this wire, we can actually calculate what is the temperature gradient and other interesting things as we'll get to. I just want to make a very important comment here that something which is particular of this kind of devices is that the thermal conductivity is non-linear. So this is going back to what I mentioned before, that at zero temperature, the superconductor has no quasi-particles to carry heat. So at zero temperature, the superconductor is a very good thermal resistor. And this changes, of course, as we approach the critical temperature of the superconductor, and the superconductor becomes a normal metal, and there the thermal conductivity enhances. So we also take into account this non-linear thermal conductivity of a superconductor. But without going into too much details, I just want to point out that by using the simple model, we can get to a very simple relation that of the voltage at which the leads turn from superconductor to the normal state. Okay, so this is what we will be calling as V-dip. So this is the voltage at which the leads turn from superconductor to normal. And one gets a very simple relation, which is directly proportional to the critical temperature, as you can see here. And there are only very few other parameters that are of relevance. So let me just comment on these two here that are in this square root. So Rj is actually the normal resistance of the junction, and this we can measure experimentally. And this R lead is actually the normal resistance of the leads, so the normal resistance of the superconductor here. This parameter is actually reflecting the thermal conductivity of the leads, right? So if you have this goes a bit with like a Wiedemann-Franz type relation, meaning if you have a more resistive lead, then you will have also a more resistive, a thermal resistive lead. But essentially, we have this very simple relation. Now, before we are able to really start extracting information from these measurements, we first wanted to check that this model is really describing well our experimental data. And we can do that in a simple way. Here also, of course, this would be the critical current at which the superconductor to normal transition takes place. And again, it follows this kind of simple relations. Yeah, sorry, I got mixed up a bit here. Here I also want to comment that, we apart from this very simple modeling, Gorm and Alfred have worked on some more complicated machinery which allows to calculate also these transfer responses, taking into account the heating effects, and by doing this, one is also able to calculate the effects of different external stimulations, like external magnetic fields, etc. The interesting things with this machinery that they have built, so they can get IV curves that can capture the underarray processes, so they can also calculate the multiple underarray reflections as well as the heating effects. So let me just show you here a comparison of our experimental data and some of their calculations, and you can see that the main features are really very well described qualitatively. Now, going back to my previous point here, so before we can really confidently extract information from experimental data, we wanted to test this model. And again, essentially this VDIP we can get directly from the measurement. And first of all, to test the model, there's one thing that we can tune quite easily and that we can measure experimentally, which is the normal resistance of the junction. So if we take a measurement at a zero magnetic field and at base temperature in our cryostat, essentially this critical temperature of the superconductor is fixed, and this is the normal resistance of the lead, which is also fixed. So if we're able to tune the normal junction, and we can do that by electrostatic gauge, then we can see if the critical voltages at which the transitions take place, they agree well with this modeling. As I mentioned before, the normal state resistance of the junction can be easily tuned by applying voltage here to this gate. And over this range that we have studied, we can tune this resistance by a factor of 3 to 4. So now, if we take a measurement of this of the device, going up to higher voltages. Again, here at low voltages, we see the usual things that have been measured for quite a long time. So at 0 voltage, we see the supercurrent peak, and then we also see kind of MAR features, multiple underarray features. At higher voltages, you can see these lines here. These are the dips, which I mentioned to you before. We interpret them as transitions of the leads from the superconductor to normal state. And you can see that these dips, they disperse with gate voltage. Now, we try to fit this to the model. As I shown before, we expect that these voltages would have a dependence with the square root of the normal resistance of the junction. So we fit these dips with the equation I showed you before. And we use a single fitting parameter per lead. So as you can see, the normal state resistance of the two leads is slightly different. And this is just a slight asymmetry in the device. But we get a very good agreement. And you can see that, essentially we can tell that these VDIPs, they follow the square root of RJ dependencies. So with this, we get quite confident that indeed the model is describing quite well the effect that we measure. We can do the same now if we replot the data now as a function of the current that runs through the junction. Again, we see these two dips here, and now, of course, the position of these dips in the y-axis, they correspond to the currents at which the leads go from superconductor to normal. And again, using the same relation here now with IDIP, so we can get again a very good fit using the same free fitting parameter. So again, just a single free fitting parameter per lead. So with this first characterization, we, as I mentioned before, we grow confident that our model is describing quite well what we're measuring. And we move on then to trying to use this effect as a spectroscopical tool. And of what, right? So as I mentioned before, one of the fun things about this simple relation is that the VDIP or IDIP, it scales linearly with the critical temperature of the superconductor. So we thought, well, maybe by taking this measurement, we can get direct information of the critical temperatures of the leads. Well, the way to do it now is we can fix the other parameters in this equation. We can keep them constant. So our lead is always constant. This, again, is the normal resistance of the leads. But then we fix the gate voltage at a particular value. And so we fix the normal state resistance of the junction. And then we want to modulate TC so that we can really show that this VDIP really scales with TC. So how do we do this? Well, first of all, what we do is to apply magnetic field. And now I want to go back to the point I made earlier on, that our wires are so-called full shell wires. So the aluminum fully covers the nanowire. in this kind of systems, there is an effect called the little parks effect, which is a consequence of the quantization of fluxoid when we apply a magnetic field parallel to this wire or perpendicular to this cross section that I show over here. And essentially, when a magnetic field is applied or a flux is applied, one sees a modulation of the critical temperature as a function of applied flux, as shown here in this experiment, this very nice paper from the Copenhagen group. So that's our approach. We want then, we have a similar type of wire. We want to apply then a parallel magnetic field. This should modulate TC in this way. And then we expect, well, we want to see what kind of signal we get from when we measure this voltage dips. Now I show you some of the experiment or the first experimental data, and already there are surprising things that we saw already from this first measurement. We do see the two voltage dips, one per lead, as I mentioned before, but the surprising thing that struck us in the beginning is that the two leads or the two dips associated with each lead seem to oscillate a bit differently. So they seem to show different little parts oscillations. We started analyzing this, and we applied an Abrikosov-Korkov theory to take into account the effects of this applied flux in the critical temperature of the wires. And the only way we could get a good fit to describe these two different oscillations was to assume that the two leads or the two superconductors had a slightly different superconducting coherence lengths. Our conclusion is that this is really an effect of disorder. In the 30 limit of superconductors, the coherence length scales with a mean-free path, and we interpret this as a reflection of fluctuations in the disorder level across the wire, which leads then the two leads to have different superconducting coherence lengths. By applying the machinery I mentioned before, the theoretical machinery, Gorm and Alfredo calculated the expected response for these type of measurements by considering two different superconducting coherence lengths. And as you can see, this can really describe very well. It's in very good qualitative agreement with the experimental data. As another control experiment, what we did was then to compare the kind of parameters we extract from this type of fittings, from the dips that we measure, with another type of measurement here. We measure the resistance or the differential resistance of the device as a function of the temperature and of the magnetic field. And over here, the white color here corresponds to the normal resistance of the device, and the blue, the regions with the blue contrast here, they correspond to resistances that are lower than the normal state resistance, and this can be due either to Josephson currents, so over here, for instance, where the differential resistance goes to zero, or to some type of Andreev processes, which lead also to lower resistances. The dashed lines here, they're not direct fits to this measurement on the right. Instead, we fit these dips here with the Abrikosov-Volkov theory, and we take these parameters, and then we just plot here the expected temperature or variation of the critical temperature of both leads. Overall, there's a very good agreement, and it's not so easy to see, but the regions in between the two dashed lines, you do see a slightly reduced resistance. So we think it captures also this physics that the critical temperature of both leads can be different for a given magnetic field. But I just wanted to comment here is that the contrast here on the measurements on the right is much more subtle than the information you get directly from the measurement on the left. Meaning, it would be hard to get to this conclusion of these different superconducting coherence lengths just by looking at the measurement on the right. Whereas by applying this kind of Joule spectroscopy measurements, we get a direct device fingerprint in a very simple and quick manner. The last question we had about this kind of characterization was if from the gain information that we get from the Joule spectroscopy, if we can use it to understand better what one measures in the low bias transfer response. So over here, I just highlight that the information that we can extract from Joule spectroscopy from this type of measurement here on the left are the dependencies of the critical temperatures of each lead as a function of the magnetic field. So again, our motivation in this last part of the analysis was to see if we can get, if this information, TC as a function of B, can be used to understand a bit better the low bias transfer response. Here I note that at zero magnetic field, we can use this BCS type relation. So the critical temperature of the superconductor is directly proportional, or it's proportional to the superconducting gap. But this is only valid at zero magnetic field. So here, these are also some calculations from Gorm showing what is the effect of an applied magnetic field. And as you can see, the density of states of the superconductor changes considerably with the pairing effects by the magnetic field. So it deforms significantly when compared to what one would expect by a BCS density of states. And the low bias features that we measure in transport, they're actually proportional then in applied magnetic fields, not to the gap per se, but actually to the spectral gap, which here in this plot is shown in green. So turns out the red dashed line here is a fit by Gorm that shows that approximately the spectral gap can be described by this relation here, which goes with a power of 5/2. Okay. So now we will look into the low bias data, which is over here. And again, the dashed lines is just information we got from the Joule spectroscopy measurement. So these are the dependencies TC as a function of B obtained from the other measurement. And then we just plot over here using this relation with the power of 5/2, as said, because these low bias features, they actually follow the spectral gap. And we get I would say a decent qualitative agreement with experimental data. So already I would say we were quite pleased that just by not including any other fitting parameter, we can get such an agreement with the low bias data. Okay, over here, I want to move on to other examples which potentially even underscore more the usefulness of the technique. So I just want to point out that this device, the one that I show you first, which we call device 8, is in spite of the differences in the superconducting coherence lengths of the leads, is still the most symmetric device that we measure. And you can see over here that in low bias, we see these little parts oscillations, but I want to just tell you that this looks actually quite symmetric, so to speak. I would say Joule spectroscopy for like the examples that or the samples that we measured, we saw that it's actually quite good for understanding devices that are very weird. So here I show a second example, which we call device B. And this is, again, the low bias response. And just looking at the low bias response, it does look somewhat like the one on the left. I mean, we see these little particle oscillations, but it's fuzzier. So there are some lines that seem to not oscillate with the same little parts oscillation. So by showing this data, I just wanted to comment that typically in a transport experiment, we would be looking at this regime, and we would look at this data, and we would probably conclude, okay, it's a Josephson junction with little parts effect, but we don't quite understand fully why it looks weird, right? Anyways, then when we apply the Joule spectroscopy, so we take these measurements with higher voltages, then we can, as said before, get a direct fingerprint. And what we can see is that one of the leads does oscillate with the little Parks effect, whereas the other one does not. So our interpretation of this is that this device, actually one of the leads is not fully covered, or the superconductor doesn't fully cover the nanowire. So this is what we concluded would be a full shell on one side and partial shell on the other side. And this is directly seen from the Joule spectroscopy measurement. Now, if we do the same trick as we did for device A and take these dependencies here and translate into spectral gaps, then we can see that indeed, like some of these peaks, they should follow the sum of the two spectral gaps. So you do see this kind of little parts oscillations, but these other lines that they don't oscillate, they are reflecting the one of the leads that is not full shell. So it turns out that this kind of samples they're not as rare as one would think. We measure a couple of samples like this. What is the origin of this? Well, it could be definitely it comes from discontinuity in the covering of the epitaxial shell, and we cannot tell if this is due to some problems during growth of the wire, some discontinuity that forms during the growth of the wire, or if during the etching of the junctions that it would etch preferentially on one side. So we don't know exactly what the origin is, but by applying this technique, we can very easily detect it. A second example, or a third example, in this case, device C, we had a slightly different geometry here. These are 4 terminals, and we had made them like this to measure the supercurrent with better precision. And over here, we used gold contacts to the epitaxial shell. And this is well, it's not an uncommon geometry that you find in the literature. Also comment here that the distances from the junction to the nearest gold contact was made asymmetric on purpose. If you want to know why, you can ask me later. It's not so important right now why we did it, but they're asymmetric. So clearly this cartoon is not up to scale, but one side is closer to the gold contact than the other. So this is relevant information. And by applying Joule spectroscopy, we see again the 2 dips here and the oscillations with little parks, and so nothing particularly different from what I was showing so far. But the interesting thing is that when we took a measurement of this Joule, the V dips here as a function of temperature, then we observe that the 2 dips, they have different critical temperatures. This is really reflecting the inverse superconducting proximity effect. As I mentioned before, one of the leads is shorter than the others, and over here we can definitely, well, we can clearly see that by this type of measurement, we can detect the different critical temperatures of each lead in a single measure. The lower critical temperature, yes, it will be corresponding to the side which is shorter or is closer to the gold contact. Let me just also say that we're not expecting such strong inverse superconducting proximity effect with these length scales. Clearly, I mean, once you think about it later, it seems obvious that there should be, but we didn't think about it before. You can see that the critical temperature drops to below 1 Kelvin, being 300 nanometers away from the gold contact. Once we characterize then the different critical temperatures and the dips, like we did it for the previous devices, again, we can get a very good correspondence then now with the measurement of the resistance of the device. So we again get a very direct fingerprint and understanding of how the device works. So with this, I just want to comment again that we believe that this technique, Joule spectroscopy, is very powerful. I mean, I mentioned several times we're getting fingerprint of devices. You get complementary information to other techniques, and that it can be very helpful also interpreting the low bias response, as we can really understand what are the properties of both superconducting leads at the same time. These results, we have put them together in this manuscript that we have uploaded to the archive a month ago. So if you're curious, please take a look. Let me just mention some implications of the kind of imperfections that we saw in our devices. So first, I want to comment on disorder. So we do see that there's also quite even large fluctuations in the mean free path along the length of the nanowire. So this is really disorder in the parent superconductor, in case in the epitaxial aluminum shell. Well, on the one hand, so I just point out this paper. On the one hand, it was already known that having disorder in the epitaxial shell is important, so that it enhances the proximity effect on the nanowire. This paper also points out that actually, if the coupling of the superconductor and the semiconductor is very strong, some of this disorder can be transferred to the semiconductor. And they argue that if this happens, this could further complicate like the conditions for getting a topological superconductor in this type of systems. The other general comment is that about the inverse superconducting proximity effect. As said, we were not expecting it to be so strong, but after you see it, I mean, it seems obvious that it should be there. So I think also another thing we learned is that this type of Joule spectroscopy characterization is useful for the optimization of device geometries. So here I show this geometry used in an experiment directed at searching for topology in these full shell wires, and where there's a gold contact here in the middle. Now, according to what we measure, we would clearly we would know that in this wire the superconducting gap is not continuous, and most likely underneath this gold contact goes to 0, which effectively cuts the wire in half. And the third implication here, which I want to stress, which I think is actually a very important one, is that heating effects are very important in these hybrid superconductor semiconductor devices. And this is really an effect that has been largely overlooked so far. This is a calculation, again, from Gorm, and on how the temperature of the superconductor would change with the voltage. Here again, for parameters similar to the ones that of our devices, and you can see this non-linear response, and this is actually quite an interesting and important conclusion, which is the following. As you can see, for low voltages, you have a very abrupt increase in temperature, and this is because, as mentioned before, at 0 temperature, the superconductor has no quasi-particles, and the thermal resistance is the highest. So even if a little bit of heat is generated at a junction, this will lead to a very substantial increase in the electric temperature of the device. As heating intensifies, then the temperature of the superconductor increases, and this generates some quasi-particles, so the heating gets less, well, the increase in temperature gets lower for higher voltages until you reach the critical temperature here. But heating can be quite important, and this is something that we want to look into more detail. Also consider the operation of hybrid superconductor-semiconductor devices in general. And by continuing this point, I just want to mention that we have noticed, and these are some data that we're currently analyzing, the heating is even more important in devices which have this kind of island geometries. So here, the difference when compared to the devices I've been discussing so far is that there are two junctions rather than one. Now, you could ask, why would this kind of geometry be interesting? So there has been work on Coulomb blockade periodicities here as also a signature for topology. And also in terms of topological applications, islands are considered for the geometries to observe topological effects, or also for the realization of topological qubits. So it's a geometry that has been studied and is important. By doing similar type of measurements, we noticed that the power required to drive now the superconducting island here to the normal state is 100 to 1,000 times lower than in single junctions, and this is reflective, we believe, to the heat dissipation mechanism. So this is data that we're currently analyzing, and hopefully soon I can tell you more about that. And just to conclude the talk in the last 3 minutes, I just want to flash a bit and do some advertisement of other things that we're doing in parallel. So as in other groups, I mean, we're also interested in implementing high frequency techniques to add to our toolbox to increase it beyond DC transport measurements. So we're doing this step by step, because this, I mean, requires also some learning curve, and we wanted to start also, well, first by measuring the impact of microarrays on DC transport, also implementing reflectometry experiments for tuning quantum dots, and then moving on to microwave spectroscopy. So this is work in progress, but I mean, we start having some results as well. So here's some Shapiro steps that we have been measuring in these devices based on this kind of epitaxial aluminum indium arsenide nanowires that I've been showing. Here's some examples of 4 Kelvin of reflectometry measurements for, again, tuning quantum dots. And in terms of microwave spectroscopy, we have an ongoing collaboration with Alicia Gomez from the Astrobiological Center of CSIC. And she's expert in superconducting circuits. So she's fabricating superconducting resonators, and we're trying to couple them to our devices. So this is work in progress. And just as a final slide, also as a parallel research line, a few years ago, we started exploring devices based on 2D materials. So this is still, I mean, we're still in the effort of improving our fabrication technology to get better materials. We start looking at some Josephson junctions based on ion diselenide and graphene devices, which also we intend to collaborate with groups from from IFIMAC, also for doing combining it with scanning tunnel microscopy. With this, so I want to thank you for your attention, and here's just a list of all our collaborations here. And yes, so now I'm open for questions.
Thank you, Edu. Thank you very much for this fantastic talk. I see that we already have a question. Akadesh, I think you can unmute yourself. Yes, go ahead.
Hi, thanks, Eduardo, for a very nice talk, very interesting stuff. I was just wondering that in the in the analysis of heat conductivity and so on, it seems to me you consider electrons or quasi-particles, right? So is it, I'm wondering, do you consider phonons at all, or is it reasonable to ignore phonons when we have a superconductor?
Yeah, so we estimated what would be the cooling power by electron phonon coupling, and we estimated it to be like 2 orders of magnitude lower than quasi-particle. So it's true, as you say, the modeling that we take into account only considers quasi-particle as a heat dissipation mechanism.
All right, okay, thank you.
Okay, Elsa.
Hello, Eduardo. This was a really fantastic talk. I also read your paper, but now I think I've understood more things. So I really congratulate you and all your collaborators, because I think it's just amazing. And we can really learn many things from these wires, which is something very important in the field. Now I have some questions related to what we can learn about disorder. So it looked to me that in the first part of your talk, the differences in the dips where the superconductor to normal transition happens, you ascribe them to different resistances of the two leads, whereas more in the second part of your talk, you talk about different coherence lengths, so different diffusive coherent lengths of the wire. So I was wondering if, so the first part looks to me like a geometrical origin, length, I don't know, radius of the wire, thickness of the shell, whereas in the second part, you go to the coherent lengths. And I was wondering if maybe the difference in the second part could be ascribed not to a different coherence length, but for example, to a different width of the, a different thickness of the aluminum layer, or how did you decide to go for one or the other?
That's a very good question. And you're right. In this first part, the differences, or the reason for which we measure two separate dips is indeed by geometrical factors. How do we know this? You could ask, right? So indeed, if we take a measurement of these dips now as a function of temperature, and then we can obtain what is the critical temperature of the two superconductors, right? And for this particular case, it's the same. It was 1.35 Kelvin, I think. So by doing this, we can fix this parameter here. And the normal resistance of the junction we know experimentally, right? So then we see these two dips, and over here, the only other parameter that we can change is indeed the normal resistance of the leads, and this is what gives this slight asymmetry. Now, to grow confident that this is indeed the case, we started making asymmetric devices, and that's later on I mentioned that we made it on purpose. The different lengths of the two leads was actually to check that this was indeed the case, and this device in particular is quite symmetric. That's why both dips are almost coinciding on top of each other. But if we make them less symmetric, one, let's say, with twice the length of the other, then we can really see that the splitting of the two dips, they increase. So we're quite confident that at this level, for zero magnetic field, this asymmetry here is due to geometrical reasons. Okay. Now, moving on to the second part. So why now we say that these changes or the different oscillations are due to the coherence length and not for geometrical reasons? Well, first of all, we take into account already the different resistances of the leads, right? So the previous asymmetry is taken into account here in fits. The second thing is then how these dips, they oscillate with magnetic field. And there, different parameters come into play. As I think, well, of course, as you know from your little parks analysis. So as you mentioned, there are many things that affect the way this oscillates. One is the thickness of the luminance shell. There's the superconducting coherence length, and there's the area of the wire, right? All of these things. So turns out that really the combination of the parameters we can vary to get a good fit. The only way really that one can fit this dependence with magnetic field is by taking different superconducting coherence lengths. So for instance, if we would change the thickness, this really changes how this drops, right? Like the height of each lobe drops with field. So anyways, the students tried, my students and Gorm were really trying to play a lot with this, and somehow it's yeah, that's the
so the best fit was indeed with the different coherent lengths.
Yeah.
And one question related to this. So you are able to see that there are different let's say mean-free paths in the two leads that turn out that then give two different coherent lengths. But in general, with your experiments, you can access, let's say, to the possible disorder in these aluminum shells, but the effect on the semiconductor, what you mentioned at the end in this paper by Stanescu and Dasarma, that there might be, let's say, a leakage of this disorder to the semiconductor. Is this is your technique able to see this or to know this? Because if I understand, all your measurements relate to the critical temperatures and gaps of the shell.
Right.
Not something directly from the core, no? Is this correct?
Yeah, so what I believe is that, yeah, you're right. The main features, this high voltage, high current features, they're what we believe is really properties of the shell, not of the core. But I think our belief is that, well, let's say the high voltage, high bias signals are related to the parent superconductor, to the shell, and the low bias will be reflecting also the hybrid device, right? So one of the things that might be interesting is really then to try to correlate the high bias and low bias measurements and see if we can understand better of the device as a whole. About the particular kind of leakage of disorder from the shell to the wire, I think that still would be difficult to measure in any way, because as far as I understand from that paper, well, you could be having, because the problem is low bias measurements, let's say tunneling spectroscopy, is very sensitive to the decay of the wave function, so it would be very localized, right, towards the end or towards the ends of the wire. And this leakage could be around the bulk of the wire, so to speak. So how to probe this exactly?
Yeah, I understand.
Yeah.
Okay, thank you very much, Edu.
Okay, I see another question by Farkad. Please go ahead, Farkad.
Yeah, okay, so Eduardo, thanks for the nice talk. I have basically a question related to dissipation in the volatile parks oscillations when you play in plane field. Basically, you drive system to zero temperature, as you see, and in principle, I don't know, I am not expert in little parks, but I suspect that there will be also heating in the moments when basically you have phase change. This is the question. And also the wire is on the substrate, and probably it doesn't touch everywhere the substrate in uniform form. So they suspect that the dissipation heat transport from wire to substrate also could be inhomogeneous. So and that question was not discussed by you.
Okay, thanks for the questions. Just to understand the first question, you are referring to heat dissipated by the transition from superconductivity to normal by the little parts effect.
Yes.
I don't know, but I'm not aware that one should be expecting this really.
Well, and that was just curiosity, if there is at all. Yeah, of course, you come to the critical current, and then as I understand that in the moment when TC drops, critical current is also high, because to get phase change in the little parks, you should increase the current which oscillates around, and this current, finally, when it comes to the critical current, then there is a phase change. So my question was, if in that point, because your fits are worse exactly in the places where you have critical temperature dips. So at some point.
Well, clearly, yes. I mean, by this modulation, you do get a lowering, and as soon as at any point during the measurement that you hit a dissipated branch, there will be heating. So there's heat dissipated, and this will be modulated also with the Parkes effect. The one thing I wanted to say is that you were saying about the feeding being worse. It's true that okay, let me maybe show this. We're showing this equation again. We have this factor here, which is this big lambda, which okay, again, for this to work, for us to get direct correspondence between the voltage dip and the TC, we need this to be constant, right? So this needs to be constant as a function of different parameters that we change, including, for instance, magnetic field and temperature and things like this, because this really carries details of the quasi-particles in superconductors and then the thermal resistance of the leads. Is this strictly constant? No. I mean, you can see this in the supplemental material of our preprint. I don't have this plot here, unfortunately. But it turns out that luckily it's very close, it's almost constant for most of the parameter space that we can study in the experiment. So also with little Parkes effect, also with the oscillations of TC, this doesn't change so much. So that's why indeed our fits are not bad, I would say, throughout the measurement due to that reason. Second question about heat dissipation, right? So for the model, we are neglecting electron photon coupling. So we're assuming that all the heat is carried by quasi-particle in the leads. Is this a fair assumption? As I mentioned in the answer to Akash, well, we estimated how important would be electron photon coupling for dissipation, and we estimated it to be 2 orders of magnitude lower. It's true that, of course, if you completely kill heat dissipation by quasi-particle, so let's say if we were able to go to 0 temperature, and then there's absolutely no cooling by quasi-particles, then that would be the dominant mechanism. So this will be a correction, of course, to the heat dissipation that we take into account. Now, the very good agreement between that simple model that doesn't take into account dissipation to substrate, I think points towards the fact that indeed quasi-particle diffusion is the main heat dissipation in the experiment. But what you said is not untrue. I mean, it's just that in the data, we don't get such detailed information about dissipation to the substrate as it's overshadowed by the quasi-particles. But it's true that there could be inhomogeneous, or it could be that there are details there that play a role. Yeah.
Okay, thank you. Thank you.
Thank you, Edu. I see no further questions, so I think we can leave it here. And thank you again for the fantastic talk, Edu.